Now that we've talked about delta G a lot, we've had a review of Hess's law, delta H, delta S, let's go ahead and talk about the free energy of a reaction, or delta G of a reaction, but if we're under non-standard pressures and non-standard conditions. We should be able to find from the standard free energy reaction, we should be able to calculate the value of an equilibrium constant, K, remember K, we spent enough time on K, and vice versa. So we should be able to discuss the system at non-equilibrium or non-standard pressures and concentrations and determine equilibrium constants and go back and forth. So first, what is the relationship between this idealized value of delta G naught? Remember that little naught symbol means standard. And the real world free energy change for a reaction. So remember, when you see delta G naught like that, that is very specific in what it means. It means that if you have a solid or a liquid, they're in their pure form. That means that if you have a gas, the gas itself is at a partial pressure of 1 atmosphere. If you have a solution, the solute in that solution is at a concentration of 1 molar. And if temperature is not specified, temp is in Kelvin, 298 K. So what does that tell me though? There is an equation we need to know. The equation we need is delta G equals delta G naught plus RT ln of Q. So delta G and delta G naught, what is the difference? Delta G is the free energy change under real world conditions. Basically, it's under any conditions. It's what we want to know. And it can be used under, again, any conditions. Delta G naught is the standard free energy change, and this is what you get from your tables. This is that 1 atmosphere of pressure for partial pressure of gases, 1 molar concentration if you have a solution, 298 K. And then R is our gas constant, 8.314 joules per mol K. But since we're dealing with delta G, we're probably going to have to convert this into kilojoules. So 8.314 times 10 to the minus third kilojoules per mol K. T is the temperature we're actually at in Kelvin. And do you guys remember Q? Hopefully you remember Q. Q is your reaction quotient. Which is what I call the products over reactants equation. It's not quite correct like that. It's your products raised to their respective coefficients divided by the reactants raised to their respective coefficients. And this is for pressures or concentrations. Solids and liquids remain constant. So this equation, you need to know. You need to know how to put the pieces into it. Let's go ahead and work a couple examples. Let's say we have a system of N2 gas plus H2 gas giving me NH3. We can see here that 1 mole of N2 reacts with 3 moles of H2 to produce 2 moles of NH3. It's a very famous process called the Haber process for the production of ammonia. It gives me the delta G here, delta G naught or delta G standard, to be negative 33 kilojoules. which means it's also a spontaneous process. So we're showing here that this is, that we have a delta G value that's negative. So when delta G is negative for this process, I don't care the value itself, I just care the fact that it's negative. It means this is a spontaneous process. So delta G is often an idealized value or hypothetical construct. Again, what is this value between the two? Well, we see that we have an equation, delta G, under regular conditions, is delta G naught plus RT ln of Q. If we're told the standard free energy change for the reaction below is negative 13.6 kilojoules, what is the value of delta G when the pressure of NH3 is 10 atmospheres, the pressure of CO2 is 10 atmospheres, the concentration of NH2CO NH2 is 1 molar, and the whole system is at 298.15 K? Under standard conditions, if I was at standard conditions, all gases would be at 1 atmosphere. Concentrations, my solutes, would be at 1 molar, and solids and liquids be in their pure form and do not affect the system. Under these real-world conditions, which is noted in the question itself, I have 10 atmospheres of NH3, 10 atmospheres of CO2, and 1 molar NH2CO NH2. So what is my delta G? I'm going to have to use my equation. Delta G is equal delta G naught plus RT ln of Q. I know delta G naught because it tells me in the question that delta G naught is equal to negative 13.6 kilojoules. So negative 13.6 kilojoules. Plus R, my gas constant, 8.314 times 10 to the minus third, because I want kilojoules here, kilojoules per mole K. Times temperature, 298.15 K. Times the natural log, products over reactants. My only product here is NH2CO NH2, and I've got a 1 molar concentration. Over reactants, those are in pressure, and yes, you can compare these two. I've got, let me just write Q up here really quick so you can see, make sure that you're not forgetting little pieces to it. Q is equal to the concentration of NH2, CO NH2, divided by the partial pressure of NH3, quantity squared, because I do have a coefficient of 2 out front, times the pressure of CO2. So that's what I'm plugging in here. My concentration of NH2CO NH2 is 1 molar. My partial pressure of NH3 is 10 atmospheres. That quantity is squared, and the partial pressure of CO2 is also 10 atmospheres. Solve this through. Now, the units look a little funky here, I know. We know that Q is unitless, so this quantity here becomes unitless. And we add all this up together. Delta G here, negative 30.7 kilojoules. Some people may say, what about the mole rate here? This value for delta G I've gotten from the table is actually per mole. We just don't record it that way because it's per the reaction. So it is a complete comparison here. We see that the overall delta G for the reaction we're looking at is negative 30.7 kilojoules. Does this answer make sense though? Well, think about what this means. What does delta G mean? Delta G means how likely is this reaction to proceed as written. Under normal conditions, under standard conditions, when everything is 1 atmosphere, 1 molar, delta G is negative 13.6 kilojoules. I have now drastically increased the pressure. 10 times higher increased the pressure of both reactants, but kept the concentration of my product the same. So yeah, we expect delta G to be a bigger negative number. We have more reactants in the reaction now, which is a greater driving force for the reaction. So, free energy and pressure. The entropy depends on the pressure of the gas. There are more probable positions of the molecules in a gas with greater volume, less pressure, than with less volume and greater pressure. The greater pressure, the smaller the volume, the smaller places, or the less number of microstates available for the system to be in. Therefore, less entropy. Greater the volume, less pressure, more possible microstates, more possible positions of the molecules, greater entropy. Free energy is also dependent upon pressure. So we can derive these equations. Delta G is equal to delta G naught plus RT ln of Q. This is the free energy at non-standard conditions, non-equilibrium. At equilibrium, delta G is equal to 0, therefore Q is equal to K. Delta G equals negative RT ln of K. How did I get there? Well, if I've got delta G equal to 0, that means 0 is equal to delta G naught plus RT ln. I'm at equilibrium, so I've got K and not Q. Delta G equals 0, Q equals K. I've substituted those things in for delta G and Q. Now I just rearrange this equation, say delta G naught is equal to negative RT ln of K. So at non-equilibrium, at equilibrium, I memorized this equation and quickly derived the other one. I don't care if you guys memorize both or not, but that's how I personally do it. I don't like memorizing equations. I know that at equilibrium, delta G has to equal 0. Why? Because if system's at equilibrium, it's not spontaneous in either direction. It's completely content where it's at, and it's going to stay there. So at equilibrium, delta G has to be equal to 0. It's not spontaneous, and it's not non-spontaneous. It just is. And I know that at equilibrium, Q equals K. Substitute that into my equation, I get delta G equals negative RT ln of Q. K is equal to Kp for gaseous reactants, and K is equal to Kc for solutions. Your gas constant is still 8.314 joules per mole K. So, some equations you've got. Delta G equals delta H minus T delta S, or you can say delta G naught equals delta H naught plus T or minus T delta S naught. What's the difference here? This is under any conditions. This is under standard conditions. Meaning this is always valid. This is only valid under standard conditions. And then we know delta G equals delta G naught plus RT ln of Q. And that's at any conditions. Any point in the reaction, we can calculate that. But if we are at equilibrium, delta G is equal to 0, Q is equal to K. Substitute that in, and you get delta G naught is equal to negative RT ln of Q. So, for any equilibrium reaction under standard conditions, again, we got our Haber process. N2 gas plus 3H2 gas giving you 2 moles of NH3 gas. Standard conditions, 1 atmosphere each. They're all in the gas phase. Figure out Q here. Q would be equal to 1.00 squared, because Q is equal to the partial pressure of NH3, quantity squared, over the partial pressure of N2 times the partial pressure of H2 cubed. 1.00, 1.00, quantity cubed, still equal to 1. Under standard conditions, Q is always equal to 1. Under standard conditions, is the reaction equilibrium? No, not always. Because delta G here is not equal to 0. Delta G is actually less than 0. The reaction is spontaneous in the forward direction. Because delta G is less than 0. If delta G was greater than 0, it would be spontaneous in the reverse direction. And quick, just summary from what we just talked about. So again, if the system is equilibrium, delta G is equal to 0. Q equals K. Delta G naught equals negative RT ln of K. If Q is less than K, the reaction is spontaneous in the forward direction. If Q is greater than K, the reaction is going to move or proceed in the reverse direction. If Q is equal to K, we have an equilibrium. If delta G is less than 0, it is spontaneous in forward direction. If delta G is greater than 0, it is non-spontaneous, but you can say spontaneous in reverse direction. And if delta G is equal to 0, we are at equilibrium. Under standard conditions, Q is always going to be equal to 1, but that does not mean we are at equilibrium. It just means we're under standard conditions. So delta G equals negative RT ln of K. When is this equation valid? If KQ is greater than 1, at equilibrium there are more products than reactants. So this equation at equilibrium, right? Does that mean that K has to equal 1? No. It only means that delta G has to equal 0 and Q has to equal K. They don't have to be at 1. K is your products. Resistors coefficients divided by reactants. Resistor coefficients. So if Kc is greater than 1, at equilibrium, more product than reactant. But under standard conditions, Q is always equal to 1. Therefore, the forward reaction is spontaneous as long as delta G is less than 0. And if 0 is less than Kc is less than 1, then we're at equilibrium. We, generally speaking, are at equilibrium. It's not a guaranteed thing. Delta G does need to be equal to 0, but generally speaking, we're very close to the equilibrium at this point, roughly. But we can say for sure that there's more reactants than products. And under standard conditions, Q is still equal to 1, though. And it will be spontaneous again, only if delta G is less than 0. If delta G is greater than 0, it is non-spontaneous. And it's non-spontaneous as written, meaning that the reverse reaction is spontaneous. Now, K is temperature dependent. We talked about that a little bit in when we learned about K in the equilibrium chapters themselves, but K is temperature dependent. So we've got delta G equal to negative RT ln of K. We also know delta G is equal to delta H minus T delta S. We can derive an equation. The natural log of K is equal to negative delta H naught, delta H standard conditions, divided by R times 1 over T plus delta S over R. And I should have written this in the equation format, but I wrote it, but I should have written with like actually showing these as divisible. But if we rewrite this, ln of K is equal to negative delta H naught over R times 1 over T plus delta S naught over R. Hopefully you recognize that this follows the format y equals mx plus b. We can use a graph to determine the enthalpy of a reaction experimentally. So if we graph the natural log of K as a function of 1 over temperature, the slope here is equal to delta H naught over R, our gas constant, and the intercept is equal to delta S naught over R, again, our gas constant. How can we use this graph to experiment to determine the enthalpy of reaction? This way, we can figure out the slope. Take the inverse of the temperature, plot this as a function, or plot this respective to the natural log of K. So natural log of K is a function of the inverse of the temperature, and we're going to get a line. We're going to get a relatively, or hopefully straight line, because we're following a linear graph here, linear format here. We should see a linear plot, and we can look at the slope, multiply that by the gas constant R to find H, or even use your intercept to find your enthalpy. Will your slope be positive or negative? What do you guys think? The truth is, it depends on the reaction. You're going to see positive and negative slopes. So how does equilibrium constant reaction affected by temperature? It depends on the reaction itself. Remember back to the equilibrium chapter, if we increase the temperature of the reaction, we treat the temperature as a reactant or a product. If it's an endothermic reaction, we treat temperature as a reactant. If it's an exothermic reaction, we treat temperature as a product. That will affect our Kc values. We also have a 2-point form of this equation that we can use. So if you're given 2 different temperatures and 1 K value, you can solve for the other K value, or 2 Ks and 1 temperature, you can solve for the other temperature. The 2-point form is the natural log of K2 over K1 is equal delta H naught of the reaction over R times 1 over T2 minus 1 over T1. Now what if I looked at these graphs here? What do these tell me? See here, I've got 3 different graphs. They all say x-axis is extent of reaction, the y-axis is your free energy, and I see I've got 3 different systems where I've got A in equilibrium with B, One says that K is less than 1, one says K is greater than 1, and one is K is equal to 1. If I look at the first one here, where K is less than 1, I've got more reactants than products present. How do I know that? Well, K is less than 1. I know that if K is less than 1, it means I definitely have more reactants than products. Under standard conditions, Q is equal to 1, and I see that this reverse reaction is spontaneous. Delta G naught is greater than 0. When K was greater than 1, that means I have more products than reactants. Under standard conditions, Q is equal to 1. And I see here the extent of the reaction, it's spontaneous in the forward direction. Delta G naught is less than 0. And I've got K equal to 1. This is truly at an equilibrium. If it is at equilibrium, delta G naught is equal to 0. So each time here, I'm looking here, my extent of my reaction, halfway through the reaction. This is a reverse reaction, spontaneous reverse reaction. Spontaneous in the forward direction and completely at equilibrium. An overall summary slide, delta H, delta S, and delta G. If the delta H value is negative, value less than 0, it is exothermic. If delta S is less than 0, it is moving towards an ordered system, which delta S does not, or which S does not like. Delta G, negative value is spontaneous. Delta H, positive value, endothermic. So remember, exothermic heat went from system to surroundings. In many systems like that, when a reaction happens, it's very likely that you're going to lose heat, because losing heat is losing that energy. It's a way to lose energy. It's a way to stabilize that system, bring it down to a lower energy state. Endothermic, heat moved from the surroundings to the system. It's moving to a state of disorder. Delta S is happy. Delta G, though, if it's positive, is non-spontaneous. Delta H, I can find delta H using calorimetry. Hess's law, standard enthalpies of formation. Delta G equals delta H minus T delta S. Delta S I can find by using your standard enthalpies table. I can use delta G equals delta H minus T delta S. And the second law of thermodynamics tells me that I can actually measure this directly. If I can go to 0 Kelvin, I can measure this directly. Delta G can use Hess's law. You can also use Hess's law here. Standard free energy values from the table. Delta G equals delta H minus T delta S. Delta G equals delta G naught plus RT ln of Q, and delta G naught equals negative RT ln of K. Again, on this, you can memorize whatever you'd like. I only have these two equations actually memorized, and then I can use Hess's law appropriately, I can use calorimetry appropriately, the tables appropriately, and I can derive delta G naught equals negative RT ln of K very, very quickly, knowing that if I'm at equilibrium, Q equals K, and delta G has to equal 0.